All right, somebody asked a question. Why are we using complex numbers to do electrical circuit analysis in AC? And I Googled that question and came up with a good answer. It's in electronics.stackexchange.com. And the question was, why use complex numbers to represent amplitude and phase? Why is it that in AC circuits sine waves are represented as complex numbers in polar form? I don't logically understand from a physical perspective why there is an imaginary part at all. Is it purely from a mathematical point of view to make the analysis of circuits easier? And then someone answered, basically they just said it's just to make analysis easier. Yes. As an example, and they give an example of Euler's formula. Someone talks about negative frequencies. We're not talking about that in this class, but there is no negative frequencies, but it's just a helpful mathematical tool. So I'll just read the answer here. Actually, the motivation is quite simple. When you have a linear circuit and you stimulate it with only one frequency, remember, when we're looking at the current and the voltage, they're both at the same frequency all the time. Wherever you look, you'll always find at that very same frequency, only the amplitude and the phase of the wave you measure change. So what you say is, let's forget the frequency. If I keep track of amplitude and phases of the voltages and or currents around the circuit, it will be more than enough. But how can you do that? Isn't there any mathematical tool that allows you to keep track of amplitude and phase? Yes, you got it, vectors. A vector has an amplitude, that is its length, and a phase, that is the angle it forms with the x-axis. Counterclockwise direction is positive. Now you could object, okay, vectors are cool, but isn't there anything cooler? Why do we need to use this imaginary unit? The answer is, the second question is easy. Making calculations with vectors is quite a pain, a notation pain. And this is a form that you can use with vectors where you're just keeping track of two numbers that are kind of unrelated. They're separated from each other. And this is like an array type of format. And this would be in addition alone. You guys can imagine like what multiplication and subtraction and division would be like. It'd be even a bigger pain. Now, you'd be drawing these brackets everywhere. It would be messy. So it says if we choose another base of IR squared, things may be better. And this base happens to exist but requires the imaginary unit j. The previous mess becomes this. And the j is what separates one part from the other part. So then it says, okay, what has an imaginary vector in common with voltage? We'll try to imagine the Gauss plane. The x-axis is the real axis. Y-axis is the imaginary axis. A voltage can be represented by a vector centered on the origin, its length being equal to the voltage value, its starting angle being equal to the phase. Now the magic trick, start rotating the vector so its angular speed, omega, which is the angular velocity, corresponds to the desired frequency. So you can see from this animation here that this vector is being rotated around the origin, and it has a certain amplitude or magnitude, and then you can see how it's being traced on the sinusoid. And I think there's it shows you in the book, but it isn't this good. I thought this might be helpful for some of you guys. And this is what we call a phasor. It's the strongest weapon you have against tough circuits. And then it's showing two voltages here with the format that we have. And if you have, let's say, three vectors, you could see how they interact with each other on the timeline, and then in the frequency domain here. So I just thought it was a cool animation, and it might help you guys to understand why we're doing this. That was it.